All right, so let's once again try to clarify this, shall we? So the biggest difference between conventional science model of conservation of momentum and draft science model is that within draft science model, direction does not matter. So when we have a system, let's say a 1 kilogram object or a ball and a 2 kilogram ball, and after collision, the 1 kilogram ball reflects back in the opposite direction. In draft science model, the value of the momenta will always be positive. No matter in which direction they go, they will always be positive, and they will always be added together to give you the total amount of momentum. Whereas in conventional science model, if one of the objects goes in opposite direction, they will have a negative momentum because direction is crucial for conservation of momentum. And now, so the conservation of momentum principle states that the total momentum of an isolated system remains constant before and after a collision, provided no external forces acting upon the system. So once again, the most important word here is system. We have to treat this as one big unified system, not as an independent 1 kilogram ball, not as an independent 2 kilogram ball, but as a unified object, as a unified 3 kilogram object, okay? One system. So let's say we are in space, okay? We are in space and we have this typical scenario where the 1 kilogram is moving to the east with a velocity of 10 meters per second. And the 2 kilogram ball remains stationary. Zero velocity, zero momentum. So the total initial momentum before collision is 10. Now we have to treat this as one unified system. This is one object. So when we are treating it as an object, we have to look at it from the perspective of the center of mass. Okay? Now, where is the center of mass located? Well, since this is a 1 kilogram and a 2 kilogram, the center of mass will always be at 2/3 the distance between them, always between 2/3. So center of mass. Now, since this one is going to the east with 10 meters per second, the center of mass also continues to move to the east, and it also does have a velocity. Obviously, you can calculate that. And in this scenario, the velocity of the center of mass will be 3.33 meters per second. All right, so the velocity of the system as a whole is 3.33 meters per second. And the momentum of the system as a whole will be mass times velocity. So the mass is 1 plus 2, so 3 kilogram. 3 times 3.33 equals 9.99 or 10. So the total momentum of the system remains 10 from the perspective of the center of mass. Okay, now after collision. So no, before I continue, so now the system as a whole, this 3 kilogram object is moving to the east with a velocity of 3.33 and with a momentum of 10. Okay, it's moving through space with 3.33. Now, after collision, according to conventional science model, the 1 kilogram ball will reflect back with 1/3 of the initial velocity, which will be, so this is after collision, the 1 kilogram ball will reflect back with a velocity of 3.33 meters per second. So its momentum is also minus 3.33, and the 2 kilogram ball will leave with a velocity of 2/3 the initial velocity, which is going to be 6.66 meters per second. So its momentum will be times 2 positive 13.33 kilograms times meters per second. So now, as this is one unified object, this means that from the perspective of the center of mass, this system is moving to the east. There's my vector. the system is moving to the east, the whole system is moving to the east with a quantity of motion of 13.33. But at the same time, it is being pulled back with a quantity of motion of 3.33, which results into a net momentum of 13.33 minus 3.33, which equals 10. Okay? Now, in what direction? Well, to the east. Since the momentum going to the east is bigger than the momentum going to the west. All right? So this means that after collision, the system as a whole will continue to move to the east with a momentum of 10. All right? So again, direction is crucial for momentum. Momentum is a vector quantity, okay? And it's important to make predictions also about the direction after collision. That's why we have to put minus and plus sinus, and it's important. This is important to make calculations and predictions about the direction of the system after collision. Okay, so in this scenario, after collision, we can calculate and predict that the system will continue to move to the east with momentum of 10. The initial momentum before collision was also 10, and so it's still conserved, right? So it's, again, why do we subtract momentum? Because the system, as seen from the perspective of the center of mass, is moving to the east with a certain quantity of motion, but also at the same time it's being pulled back with a certain quantity of motion. So we have to subtract that. It's the same as, once again, a person standing on a treadmill. The person is moving to the right with a velocity of 5 meters per second, but at the same time he's standing on a treadmill which is going to the left with a velocity of 5 meters per second. So his net velocity will be 0 meters per second. This does not mean anti-momentum. This does not mean undoing momentum. This does not mean canceling out momentum. The individual momenta remains exactly the same, but as seen from the perspective of the center of mass, the momenta undo each other because it goes to the east and at the same time to the west, being pulled back. So it's not momentum, it will be 10. Again, the same with the person. His momentum, his velocity is not cancelled out. He's still moving to the east with a velocity of 5 meters per second, and the treadmill is still moving at 5 meters per second to the left. So their individual velocities are still happening. They do not cease to exist, but the net velocity is 0. So now in your model of conservation of momentum, you say that after collision, the 2 kilogram ball can only leave with half the velocity at best. And in a more realistic scenario, it will go less than half the velocity. So if this one is initially moving to the east with 10 meters per second, and after collision, in your model, this one will go less than half. So half is 5, so less than half would be, let's say, 4 meters per second to the right. That's going to be your velocity. And so its momentum would be 8. And then this one, in order for momentum to be conserved, in your model, this one would have to have a momentum of 2. And so its velocity would be 2 meters per second to the west. Now, my question is, in which direction does the system as a whole go, as seen from the perspective of the center of mass? So this now means that the system as a whole is moving to the east with momentum of 8, but at the same time it's being pulled back with momentum of 2. So what is its net momentum? Well, logically it would be 6. It would be going to the east with momentum of 6. And that would mean that momentum is not conserved. However, you will say no. Positive 8 plus positive 2 equals 10. Momentum is conserved. But in what direction does the system as a whole move then? Okay, I mean, logically, then the 1 kilogram ball would have to be moving in this direction as well, with momentum of 2. Then it would be correct to say, yeah, the system as a whole would be moving with 8 to the east and also with 2 to the east, and that would give you a total momentum of 10. So, but in the case where the 1 kilogram reflects back, then this is false. This cannot be true. You cannot be moving to the right with momentum of 8 and to the left with momentum of 2 and still say that the system as a whole is moving to the right with momentum of 10. That can possibly be true. So what I'm saying is that your model cannot make accurate predictions about the direction of the system as a whole after collision. It will only make sense if both balls move in the same direction, but when one of the balls reflects back in the opposite direction, your model fails. And you cannot make accurate predictions about its direction. When you have a system going to the east with a momentum of 8, and at the same time going to the west with a momentum of 2, then after collision, then how the hell can the system as a whole be moving with a momentum of 10 to the east? Because the net momentum would have to be 6, not 10. Question mark, question mark, question mark.